Good afternoon. I'm Ian Coley, the Director of Advanced Computing and Simulation at AWS. That's a fancy way of saying all the high-performance computing workloads on AWS belong to my team. I want to thank you for making the trek out here to hear my session. Before we start, I would like to ask a few questions just to gauge the audience. How many people is this your first reInvent? Please raise your hand. Oh, great to have you here. How many people have been to the supercomputing conference? Great, thanks for coming. I think it's really interesting to see how these communities have come together. If I would have asked this similar question when I started at AWS 7 years ago, these would be, let's say, a Venn diagram with no overlap, okay? There would be the supercomputing crowd and the cloud computing crowd. And I think both sides were unsure about what exactly was going on the other. And especially from the supercomputing side, they were extremely skeptical if the cloud could ever handle their performance of their workloads. Now here we are, 2024, and we'll go over some of the innovations that we've brought about in this last year, but I'll also talk about our general strategy and how we think about high-performance computing, and hopefully get you a little bit excited about how we're going to continue to innovate on how we support our high-performance workloads on AWS. And one of our customers from the National Renewable Energy Laboratory will come up here and talk to you about their cloud journey and what that's been like migrating workloads to AWS. So as I said, we're gonna talk a little bit about how we think about HPC. Michael's gonna come up and give you some real-world examples. And then I'll close with a little bit about how we've been continuing to innovate with our partners. But just as an overview to kind of set the stage, what do we even mean by high-performance computing? What is this? And it can be kind of a nebulous term depending upon who you ask. And I think the problem is that HPC has become so successful at the scale of the workloads that it's been supporting. And you can see anything from auto manufacturing, doing CAE workloads, computational fluid dynamics on aerospace, from numerical weather prediction for climate support, for energy resources, looking at reservoir simulation, financial services, doing end-of-day risk calculations. It's a very broad industry. And so as we think about this, we really want to take a workload-centric approach is how we think. And when we work with customers, we look at ensuring that we're able to effectively support their specific workload on AWS. And that's one of the beauties about our composable architectures on AWS is we don't have to come up with a 70% solution that's optimized for maybe a best fit of a number of cases of workloads. We can actually help you create a bespoke architecture for a dynamically instantiated cluster that is tuned to even a portion of your workflow. Then shut that down, instantiate another portion that's, say, maybe accelerated instances, perform that calculation, shut it down. You're not tied to some monolithic architecture. And that's the power of what we offer with the flexibility of HPC on AWS. What does that flexibility give you, though? Because the way that we think about HPC traditionally has been all about innovation, right? The reason that this specialization in hardware infrastructure, networking, and storage for high-performance computing was even thought about is a bunch of people were trying to solve really important, hard, technical science and engineering problems. And they couldn't find the underlying hardware and software to support it. So they had to start building it. And what we've seen along the way is that the industry has grown almost into parallel tracks of where you have the continued scientists and engineers that are still about solving those hard problems, but then you had a subspecialty of the people that focused on the software and hardware to help them solve those solutions. And what we've seen is in a traditional approach is that you had to go through a lengthy procurement process. Then, once you had hardware procured, the scientists and engineers who are the users of the system had to then compete for time on the system. I've even recently talked to a customer this week who had to wait in a queue for 6 months to get their research project run on their system. I mean, think about how much technical innovation that in some cases could be life-altering is stuck waiting on resources right now. How do you put a price on that? Then we look at the other side when we've got elastically available resources from AWS, and you tighten up that cycle of innovation to where a researcher can think about an idea, instantiate the resources they need to test that hypothesis, test it, evaluate it, shut down the resources, and then come up with a new idea, thereby increasing the pace that they can work at. And that's why I think it's so crucial to think about how you can reimagine your workflows in a dynamically allocating hardware infrastructure environment like the AWS cloud. And at the end of the day, why are we doing all this? We're doing this so that we continue to move the ball forward. We continue to innovate. We continue to not just innovate on the scientific and engineering aspect, but on how we approach thinking about science and engineering. And in this aspect, we want to leave a better legacy than what we inherited, and we really think that the flexibility of the cloud is one of those key enablers. I'm a retired Navy guy, and so also having a long-time career in tech, Rear Admiral Grace Hopper has been one of my personal heroes. And here, I love this quote from the Admiral because she is basically saying it's okay occasionally to break stuff and to maybe do things in a non-traditional way. And why I think this applies so importantly to high-performance computing is we've had decades of people looking to experts that have said, this is the way that you perform your workloads. You build this hardware box, you maximize how you use that hardware box through important utilization algorithms with scheduling those resources, and that's it. But what happens when you're operating in an environment when you blow open that box and you're no longer constrained by a single monolithic hardware architecture to try to solve all your problems, but you can actually think differently with composable resources? And so as I lead this HPC organization and I think about the future of high-performance computing, the vision that I always share with my team, and I continue to reiterate this, is something that I call Project Any. And if you take away anything else from my presentation, please note this. This is our guiding star, okay? Ideally, we want anyone. It doesn't matter if it's a Fortune 500 engineering application developer, or a graduate research scientist, or a intern that's in a dorm somewhere. We want anyone, anywhere. They can have a mix of on-premises resources, cloud resources, entirely cloud resources. Doesn't matter, with any workload, any time. We want to really blow open the constraints to innovation and ensure that we have the ability to give people the resources that they need to really jumpstart future innovation. And of course, we want to add the tools so you can have business logic and everything, because one of the things that then the people writing, we used to call them checks. Now the people doing direct deposits or whatever to pay for their accounts are doing is, hey, if we give unconstrained access to all these HPC resources in the cloud, I might have this one scientist that just blows my budget for the whole year in 3 months. And that's one of the, I'd say, the common fears that I heard in the early days. But with the cost controls and the mechanisms that we put in at AWS, we give you the ability to put in the constraints that you want depending upon your business logic, and also the ability to remove them. Like maybe it's an important time to allow customers to burst in your workload. Maybe it's an important time to really watch spending very closely and to constrain those. But we'll give you those tools to where you can allow innovation at the pace that you want, but to still monitor costs and to control them in a manner that will keep you happy with the people that are paying the bills. What's really happening in the broader landscape of HPC? And this is something that I think has been especially fascinating to watch over my tenure at AWS. As I said, there was initially this non-overlapping Venn diagram of kind of the supercomputing people and the cloud computing people. And now we're seeing this rapidly increasing migration of traditional high-performance computing workloads from on-premises data centers into the cloud. You see here, last year alone, it was 20% of all HPC workloads had already migrated to the cloud. And Hyperion has estimated that over the next 3 to 4 years, that will increase to where 1/3 of all high-performance computing workloads are performed in the cloud. And we envision that that will continue to grow. And where we're seeing some really interesting things too that signal this is that funding agencies and facilities that typically before would be asking for a monolithic on-premises architecture, as they were drafting an RFP would say, okay, it has to meet these certain specs, it has to be these size, power requirements, et cetera, are now completely redrafting those to say, okay, we have a need for a portion of that workload for whatever particular reason is, specific latency requirements, some security questions, that they want to have a portion of it in raised floor tile space that they control, but they're really shrinking that down compared to what they had previously, and then adding in elastic cloud budget to support the rest of their workloads, giving their researchers, engineers, scientists the ability to have flexible compute that is in the AWS cloud. I want to go through a little bit of our architecture, how we have these layers within AWS. We'll go through the orchestration layer. I'll especially talk about a new service we released earlier this summer called AWS Parallel Computing Service, or PCS. And then I'll go into our purchase options. How do you actually purchase the underlying compute? What are the options available to you as a user? And then, kind of like any good HPC system, I'll review computing, network, storage, and how we've innovated in each of those areas. So let's talk about PCS. PCS is our new fully managed HPC as a service offering. Now, what we envision there is a whole family of job schedulers that will allow you, as a previous on-premises customer, to take your existing scripts and with minor modifications, move them onto AWS without having to think about, oh, I used to do this in Altair PBS Pro. How do I convert it to a scheduler that is running on AWS? We're starting this with Slurm because as an open source project, it is the one that's most easily to integrate with. But as I said, we envision expanding this to future schedulers in the coming years. And so what this allows you as a user to do is with the same API integrations, CDKs, AWS APIs, the things that AWS is known for, to dynamically provision clusters with this fully managed Slurm offering in this initial case. And not have to think about head nodes, managing resources, et cetera. Now, the actual compute nodes themselves, while instantiated by the service, will run in your account. So that's where the cost accounting comes in and where you're able to control your spend. But the actual scheduler and the management of those resources will all be handled within AWS PCS. Again, why are we creating this family of schedulers? Is we want to remove any friction that we can that is keeping customers from migrating these workloads onto the cloud. I mean, when I initially started talking to HPC customers, we had questions about performance. Can you actually perform my workloads on AWS? We've proven that. We'll go into some of the reasons why when we go into the compute instances we've created. Then it was, okay, is your infrastructure really secure enough? Well, then we went into the details of our Nitro card and how we believe, and not just us, but many national certifications have demonstrated that via the AWS Nitro card, our resources are actually more secure than on-premises data centers. So then it got to, okay, but are you actually price performant? And we get into the purchase options, I think you'll see that we have compelling offerings that can reach a price performance option that most customers would be extremely satisfied with. Here's a little bit of the specifics of a typical architecture we see from customers using AWS PCS. So as I mentioned, we see while some customers are all in on cloud, are getting out of the data center business and want to migrate all their workloads onto AWS, in HPC, there's still a majority that are keeping whatever that platform might be, some sort of footprint on premises. And so they're getting a direct connect into their data center that is then connected to the AWS cloud. And then they're integrating their virtual private cloud in AWS into their system to perform their high-performance computing workloads. What is PCS good at? Well, this is one of the key differentiators, and I'll talk later a little bit about our current parallel cluster toolkit. But one of the key differentiators, I'd say, of PCS to our previous offerings is the ability to on-the-fly update. Previously, you had to really work hard to, if you wanted to do anything from a security patch update to a new OS version, any type of perturbation to your HPC cluster required you to shut everything down, start over, spin it all back up. And since this is a fully managed service on AWS, we've reduced that tremendously to now with very minimal user impact, you can update your systems, again, be that for performance reasons, for security reasons, or for just keeping up to date on new versions. When we were building PCS, we had 3 different persona in mind. And this is where I think it's really interesting to share how we think about new services at AWS. Is really we had, okay, we've got our ultimate end user. So we've got the HPC research scientist or engineer that is trying to use these resources, that is doing these calculations. And that's kind of the easy one to think off the bat, of like the person that's using the resources. But that's not the only customer of a service. You have continued need for HPC system administrators. I mean, that's been one of kind of the, I'd say, the boogeymen also of, you heard from, I'd say, traditional on-premises people was like, oh, you're going to move everything into AWS and you're not going to need HPC system administrators. Now, you may have different qualities that you're looking for in HPC system administrators. You may need people that are now looking at, rather than racking and stacking hardware, but how do I work within AWS and cloud principles? But you still have a need for someone that is there to help create the overall architecture or to instantiate the business rules that you're creating to ensure that your customers, internal customers, are able to use resources within cost parameters that you define. And then another one that people don't always think about is when we build services at AWS, we're not just thinking about our kind of frontline customers, but we have tons of partners that build additional capabilities on top of our services. So in this case, as we're building PCS, we're really thinking about how can we help make it as easy as possible for those next level partners to build capabilities that our customers will find valuable on top of it. And this is one of those cases of who's it designed for? Well, pretty much everybody. If you're doing any type of high-performance computing, ML workload, you can use a parallel computing service. Where does it fit in our portfolio? This is a new addition to our orchestration level. And while it can do anything, what's it best suited for? Well, kind of waffling again, it can do everything. Now, again, I put HTC on here with the idea that we're talking about parallel computing service as our strategy of managing multiple schedulers. Now, is Slurm the best thing for HTC workloads? Not the way it is right now, but our vision is that future instantiations of PCS will be able to handle these high throughput computing workloads with very short duration bursty jobs. And then one thing I do want to leave you with is while we didn't have this at our initial launch earlier this summer, very soon, the team promises me, you will have CloudFormation support. It's in final testing, and you should see that very shortly, which obviously is making life a lot easier for customers to build upon. Okay, now quickly, PCS isn't the only thing that we have, right? We have AWS Batch, which is our cloud-native scheduler, but for containerized workloads. So where you have PCS as kind of standardized way of interacting with virtualized or bare metal EC2 instances, AWS Batch is for those customers that are comfortable containerizing their workloads. And you can see here, we support not only Kubernetes and EKS, but ECS is kind of one of the primary ways that customers use AWS Batch to scale up to thousands and millions of vCPUs. So this is tremendous scaling and tremendous efficiency of bin packing jobs in these containers. And we've seen customers do some pretty impressive things, from mapping genomes to develop sequences of potentially cancer-treating substances. It's just phenomenal if you just Google AWS Batch scaling, some of the things that our customers have been able to create. But if you want a serverless experience, we also support AWS Fargate, so it's a quite flexible product. We added a couple of things as key innovations this year that customers, I think, specifically value, and one of them is the ability to run sidecars. So previously you had to really orchestrate things within a single container. This year we added the ability to support multiple containers in AWS Batch. That's been especially valuable to those customers that are in robotics or are doing autonomous vehicle simulation, where they've got a workflow that requires multiple containers. And another one that this has been I've been bugging the team for this for a while, and so I'm really happy to see this, is when you've got these massive scale jobs that you're running hundreds of thousands or millions of vCPUs, if for some reason you get a job that's just wonky for whatever reason, that's blocking the front of line of the queue, that just really drags your performance down. And so previously, you might not have any insight into what's going on. Why are my jobs not continuing to schedule? I've got these resources available. It seems like they should. And maybe you've just got one job that's kind of mistweaked, or it doesn't have the specific requirements that it needs to run, that is holding up the whole rest of the pack. And so now we've given you the tools to have visibility into that and to really make sure that you can then delete that job and move on and clear up the queue so it can start exercising jobs again. I talked about Parallel Cluster was our initial foray into helping customers develop their HPC clusters on AWS. It's an open source toolkit. We're going to continue to maintain and develop it, but our focus going forward is going to be on AWS PCS, and we see customers really pushing us for that fully managed service. And then Research and Engineering Studios is an interesting way that customers have looked to really establish VDI instances. So great, I've got this HPC system. I want to try to talk to it. But what do I do with all my user workstations? And so Research and Engineering Studio is an open source toolkit that allows customers to instantiate those VDI instances that are talking to their system. And one of the key things is right here in the middle of the presentation is it's fully integrated with AWS's managed Microsoft Active Directory. So you can control the access to these resources just like you do anything else with user groups is via Active Directory. Okay, I talked a little bit about, we've got lots of options for purchasing EC2. How do you think about that? First one, on demand. That's pretty self-explanatory, right? I need a resource, I click on it, I need it right now, it starts up, I've got a certain level of pricing. Second one, which we see the majority of our customers going with, is savings plans. Okay, I'm gonna make a 1 or a 3-year commitment, so I know that I'm gonna use this level of resources, and I'm gonna get a discount based upon that. Third one is spot instances. So this is our excess capacity, where you get an extreme level of discount because we have this hardware, but when you think about just the various use cases and customers that we have globally that are using instances, we hit some troughs. And so we have some excess capacity that we're gonna pay, that we're gonna give you a large discount so that you can operate on them. And then the new one that we added recently because of the challenges around getting GPU capacity is capacity blocks. So I want to talk a little bit about capacity blocks. Capacity blocks allow you to pick a GPU window and to say, okay, I'm going to need it for this many weeks. We've now extended it up to 6 months. And I need this number of instances. And one of the things we just added too is there was a fear of like, okay, great, I do a capacity block for 2 weeks and I get to where I've got a day left and I realize, oh no, things aren't wrapping up as quickly as I'd hoped they would. What do I do now? I'm going to lose all my instances. And so we'll have an ability to extend those capacity block reservations when you get to the end, just in case, so you can wrap up any workloads that haven't completed. So what do we see customers using capacity blocks for? Well, they're using it for the things that they would love to use on demand for, but because of supply chain constraints, we just don't have sufficient on-demand capacity for GPUs. That's the honest point of it. And so we're trying to come up with this formulation of capacity blocks so that customers have a way to access these resources that have become so hard to get. Okay, let me fly through a little bit of then what's the underlying infrastructure at AWS. EC2, our Elastic Compute Cloud, has over 850 instances. I'm going to just let that sink into your head a little bit. 850 different potential types. So when I talked about a 70% solution that maybe you have to get the exact right node type if you're coming up with an HPC system, now you can micro-optimize portions of your workflow with the exact right core to memory configuration specific to that portion for a small cluster and then shut it down. I mean, you can, and it doesn't cost you anything hardly at all to experiment with it, whereas opposed to previously, you'd have to at least buy one or two, you'd put them in a lab, you'd do some benchmarking or something like that. Now, okay, I want to even see if my code can be accelerated, for example. Well, let me get some capacity blocks. Let me try it out for a week or two. I'll experiment. Okay, did I see the performance gains that I was expecting from accelerating my codes? How do I calculate that price performance now on these GPUs versus what I was getting on CPUs? And this is a specific way that we see customers using different instances. I do quickly want to talk about our Graviton 4, which we launched earlier this summer, because of it's so darn cool. It's 7-chiplet architecture, and it's the next evolution of a system that we started back 6 years ago. And you can see how with each generation of ARM architecture, we've drastically improved not just the performance, but the performance per watt. And that's one of the things that customers are extremely excited about, is the ability to use high-performance computing resources. Now, not every workload and not every code has been made to run on ARM, but we're increasingly seeing a large number of them porting to that, and I think we're going to continue to see that grow over the years. And one of the specific instances that we recently released built on this new ARM chip is the i8G, which is just a beast of a storage compute instance. It's not specific to high-performance computing, but I wanted to show it as one of the areas of innovation that we continue to demonstrate with that Graviton 4 roadmap. Okay, again, it's not just compute. If you're going to do an HPC system, you have to have network and storage. Networking, for those of you that aren't familiar with our Elastic Fabric Adapter, or EFA, it is our low latency interconnect that gets you that sub 10 microseconds latency. For any of you that heard Peter DeSantis' talk on Monday, and if you didn't, please get the YouTube version of it and watch it. He goes into a little bit of detail about what we call our 10P 10U, or 10 petabits per second, 10 microsecond, sub 10 microsecond latency network that we use for HPC and ML resources. And what that does is it's an OS bypass, so it allows you to get an extreme throughput with that low latency, so you get that inter-process communication that you expect for many of the HPC workloads, especially MPI jobs. And again, I have to brag a little bit. If you look at the right part of the slide there, almost perfect ideal scaling of these instances, which is something that I think many of my colleagues early on would have been very skeptical if you'd ever see that in AWS. And then finally, storage. We have multiple FSX options, including NetApp for ONTAP, as well as OpenZFS. But our most popular, given the popularity of it in the overall HPC architectures, is FSX for Lustre. And so customers have been using Lustre for decades. It's kind of the workhorse, open source, high-performance file system for HPC. But one thing they asked us for is, could you offer us a fully managed version? And not only that, but we really are pushing up against some of the metadata requirements with some of our larger systems. And so, similar to how you could dynamically allocate compute, now with Lustre you can dynamically allocate storage. Spin the system up. What we see customers doing is hydrating their data from S3, which is a lower cost storage. Now you've got a POSIX compliant file system that your traditional applications can operate with. You finish the workflow. You don't just shut down the compute, you shut down your storage too. You've got a fully dynamic cluster. And one of the customers that's been using Lustre a lot, and this is a really interesting use case, is for their AI/ML training, and Adobe, with their next generation Firefly models, did this all using EKS and Lustre and EC2 instances. And you can see they had a 20 times scale up in their modeling. I mean, just think about that. Where else can you get that type of scale up? And we just announced this recently. This improvement to FSx for Lustre is the combination of that EFA, that low latency interconnect that I talked about. Previously, Lustre did not run on top of that. Now, just this year, we've added that capability to run your Lustre file system over EFA and with tremendous performance improvement. And we're going to continue to innovate to improve the IOPS, to improve the metadata, and to improve the overall throughput of the system. And then finally, I'll leave you with Amazon File Cache. That's a system that customers use to put a high-speed cache. You can put it in front of a file system on AWS or file system on premises to allow you to cache your data more quickly. And I know that was kind of a whirlwind overview of our system, but I wanted to give you more time to hear from Michael at NREL to talk to you about what they've been doing there in their cloud journey. Michael?
Thanks. Thanks, Ian. That was awesome. So like you were saying, my name is Michael Bartlett. I'm a cloud engineer at the National Renewable Energy Laboratory, although that can be a bit of a mouthful, so we're typically just referred to as NREL. So I've been creating clusters in the cloud for a couple of years now, and even gotten some help from AWS from time to time. So based on that experience, they gave me the privilege to help beta test the parallel computing service a little bit from the end user perspective. And along with that, they also invited me out here to talk a little bit about how my organization has used HPC in the cloud for our research, and basically how that's shaping up the future and how PCS fits into that overall picture. So a little bit of background for anyone who isn't familiar with us. NREL is one of the Department of Energy's national labs, of which there are several spread throughout the country. And as the name would suggest, we primarily focus our research on green and renewable energy technologies and the myriad of problems that coincide with making these technologies more commercially viable. So things like smart grid technology, energy storage, things like that are all something that the lab looks at and researches. So where I fit in the broader organizational scheme at the lab, so my team is part of the Advanced Computing Operations group, and that group's focus is to try and simplify access to different scientific computing technologies for our researchers who often don't have the time or the budget themselves to become solution architects, software developers, sysadmins, things of that nature. So that's something that that group looks at. And then my team, the cloud operations team, we're within that group, so we share the same mission, but with more of a specialization towards facilitating access to cloud computing technologies and the plethora of different services that now exist within those. And another great feature about our org structure is that we're directly adjacent to our HPC operations team, which are the folks that maintain our on-premises HPC system. So that's great because we can interface with them on a regular basis, and that helps make sure that we have a cohesive and unified vision for how we're kind of establishing access to these different computing paradigms and making sure we're doing so consistently, and increasingly how we're looking at the hybridization of these two platforms. And I'll talk a little bit more about that in the coming slides. So a little bit more about my team, the Cloud Ops team. Probably the most interesting part is that we work for the researchers at our lab. So this usually looks like directly consulting with them and actually understanding their science and the problem that they're trying to solve and translating that into an effective and optimal architecture. So this is just a couple of the categories of service areas that we've been able to help projects with historically. And as you can see, it kind of covers the gambit of what's available in the cloud today. But one thing in particular to point out here is that my team, at least in its conception, has been around since 2012. So we've had a long time to hone that intuition for how do we talk to researchers, understand their science, and convert that into an effective architecture. So our on-prem system has been around for a similar amount of time, with the emphasis there being for over a decade. And due to some institutional factors, it tends to be the de facto compute platform for any researchers that have an advanced computing need. So with these two facts combined, the one being the system has been around for a long time, and the other being that researchers have tended to use it, this means that the skill set for using the HPC system is pretty ubiquitous amongst our researchers, and it's deeply entrenched into the culture. So this is a great thing because this means most researchers have this skill set that we can draw on as far as using HPC, and if we can interface with that skill set, then we can expand the platforms that they can take advantage of without increasing their cognitive burden. So they wouldn't have to learn like a new language or configuration or radically change their workloads, anything like that. So as far as identifying where HPC on the cloud was a good fit, as you can probably guess ahead, this creates a pretty organic entry point for cloud-based clusters to play a role. And in examining where they were going to be optimal for us, we thought we'd look at what are some of the challenges with the on-prem HPC cluster that folks have been experiencing. So as with any hardware purchase, at the moment of procurement, you're fixing that hardware and its capacity over time, which is just a slightly less flexible situation than what you can get with the cloud. And if you're a researcher whose workload isn't particularly well addressed by the existing HPC system, that's not exactly a fun situation to be in. Another pain point is maintenance periods. As with any server in any data center, it's going to need to be periodically taken out of service in order to do operating system upgrades or hardware maintenance. And those are good things, but it does necessarily mean that that system isn't performing the service that you purchased it to be doing. And this last point here may be a bit more specific to us as a science institution, but there was a recurring concern about accessibility to HPC systems since, again, given that ubiquity of access to the HPC systems for some of our researchers who are software developers, they're maintaining these libraries that are HPC native, generally because they're doing some kind of simulation where having that compute assumption baked in just makes sense for performance reasons. But you do run the risk of filtering out potential end users who would otherwise be interested in using that software, but they don't have access to their own HPC system. So when we were consulting with some of our projects over time and trying to identify, hey, would a cloud cluster suit your needs, we noticed that in the broader category of high capacity compute workloads, that things tended to divide pretty cleanly in these two categories. One being your HPC style workloads, the other being these high throughput style workloads that tend to benefit from a more cloud native approach. So the HPC style applications are generally pretty easy to identify. They need to pass messages between the individual runs, or they rely on a performant file system that supports concurrent I/O. And the biggest tell is if they've run on an HPC system before. So it's a bit of a no-brainer for these. You just can create a cluster using one of the cluster management services and get that job up and running. And then there are a couple of workloads that tend to be more loosely coupled, more embarrassingly parallel, that we can use a more cloud-native approach for, and you generally see benefits not only in terms of flexibility, but also performance with these. So, for example, if you're given a container-type workload, you can use one of the container orchestration services like AWS Batch, like Ian mentioned, or Kubernetes, and even better, if the job fits in a Lambda runtime, then you can just slap step functions on top as a pretty simple way to grant a concurrency layer to that. So as an example, here's a workload that we were able to help out with this cloud-native approach recently. And the details here aren't super important to get the big picture. But basically, this project was trying to map solar radiance information onto the tops of building rooftops using a LiDAR data set, which was available in an open S3 bucket. So their workload was already a Lambda runtime, so it just made sense to try and see if step functions was going to be a good fit for them. And so they read in this open data set, they process where the rooftops are, apply the solar radiance information to help get a understanding of the photovoltaic potential of those rooftops in a particular region, and then they wrote it out to their own S3 bucket and wrote some software libraries that make accessing that bucket a bit easier for end users. But the overall point here is we could have helped this project by creating them an HPC cluster, but it honestly would have been a little bit overkill and would have had to make some sacrifices in flexibility, designing a compute node image, making sure it had the supporting software libraries, slightly less flexibility in how could we scale this concurrently compared to step functions where you can just tell it how many concurrent runs you want. So if this is an example of where cloud-based HPC wasn't a good fit, that sort of begs the question of where has it been a good fit for us? So these are some of our successes, and a thing to point out here is most of these were done using the Parallel Cluster tool, which it's just been around for several years compared to Parallel Cluster, which launched back in August, so we've just had more of an opportunity to use it and incorporate it into our solutions. So these 2 points here at the top kind of are related to queue congestion and access to the system in general. There are situations that arise where a project needs to bypass our on-prem queue, which is generally, the wait time is around several days to weeks at a time, and sometimes projects can't afford to wait around for that long if they have a deadline coming up or something. So we can work with them to design a compute node image that suits their needs and kind of craft a bespoke cluster for them, and then they can run their workload without worrying about what's happening on-prem. And same with the next bullet, more of an extreme version of that situation where since our on-prem system is a finite resource, there is an approval process where projects request access in a certain amount of time, and some projects get approved for certain amounts of time and others don't. So rather than those projects who don't get approved just not being able to get any work done, we can perform the same operation for them, craft them a bespoke cluster, and then they can keep running their workloads without doing some sort of drastic refactor. And this last point here addresses that specific challenge I mentioned a couple slides ago, where some of the software developer teams that maintain open source libraries that are HPC native, a handful of them we've seen include a sample configuration file for Parallel Cluster and a little bit of documentation to help an end user spin up an ultimately modest but nevertheless workable HPC cluster and be able to try out their software and also scale it up from there if they're interested in that. And another small asterisk to this point is we are a science organization, so reproducibility matters to us. And a couple of projects that have used Parallel Cluster to run their workload, we've also seen them include just their entire configuration file. So if someone wants to recreate the results, they can create an identical system based on what they were running with. So our use of Parallel Cluster informed a little bit of what features about Parallel Computing Service in particular were exciting to us. So first and foremost is the integration with infrastructure as code. Like Ian mentioned, it's going to launch with CloudFormation support soon, and I'm sure the other infrastructure as code tools aren't too far behind. So this is great because Parallel Compute Service, while a great tool, is a separate software utility that you have to install, and its configuration syntax can be a bit dense considering the problem that it's trying to solve. So it does have a bit of a learning curve to it, whereas with the infrastructure as code for Parallel Compute Service, if your operations team is already using these types of tools and familiar with them, you don't need to install anything extra, and you can already leverage your existing skill set there to create clusters. Similarly, with the SDKs for AWS, if you don't need the full sledgehammer of state management, then maybe you're writing a web application or an event-driven pipeline to modify cluster state, then those would be a good use case. Another thing that my team in particular is pretty excited about, since we've been investing a lot of effort into empowering our clients to be able to help themselves and spin up their own infrastructure without my team being as much of a middleman, is being able to provide access to the Parallel Compute Service console. Since it is a bona fide AWS service, it will have a console view. So we're looking into granting sort of a least permission form of access to that console where they could theoretically be able to spin up their own clusters on demand. And this last point is just sort of the general benefits that you get from AWS managed services, where you generally spend less time managing and maintaining the individual components of the system and more time just using the system. So now that you know what successes we've enjoyed and what's exciting to us about the Parallel Computing Service launch, I thought I'd talk a little bit about what's in the near and not so near term for us in terms of what we're planning. First point is kind of a rehash, but it also includes the addition of IAC modules and different scripts and utilities, since researchers tend to be diverse in how they like to get work done and what infrastructure they spin up. So just making sure they're fully supported and ready to get running with that service. The second point here is the sort of hybridization effort I alluded to at the beginning, where we're interested in crafting a hybrid type scheduler that integrates with the on-prem scheduler and can burst out appropriate jobs to the cloud as necessary. So we've put in some effort to characterize different workloads on the on-prem system to see what are good candidates. And they tend to be these low resource jobs that don't really stress out the hardware in a meaningful way. And so they're just kind of noise for the on-prem scheduler and makes its job harder to allocate enough nodes and resources to run those larger jobs that the on-prem system is really great for. So the idea here is we can burst these smaller jobs out to the cloud, free up some resources so that the on-prem scheduler can run those large jobs sooner and more frequently, and everybody wins. And then another side benefit we're eager to observe with that setup is maybe lessening some of the disruption of some of those maintenance periods and have some jobs continue to run even when there's sort of a service period while they're working on the system. And then the last point is being able to expose certain exotic hardware. If, say, for example, a researcher is interested in using an EC2 instance that's purpose-built for machine learning, as an example, then we could create a bespoke partition on the fly and they'd be able to use it, and hopefully it'd be a little bit easier than just spinning up an EC2 instance on the fly, since the scheduler is going to be closer to their code and to their data. And then this last point here is just more of a philosophical goal for what we're trying to implement in the long term, doing our best to help automate some of the right sizing and try and abstract as much as possible the researcher's workload from the actual execution platform. This might include some sort of machine learning model to predictively characterize their workload before it actually executes and help suggest, which compute environment is going to be the best for it. So yeah, that was pretty much the quick tour of what my organization's been able to accomplish with cloud-based HPC. And if you have any questions, I think we're taking those at the end, but in the meantime, I'll let Ian wrap up.
Thanks, Michael. I hope that you appreciated that specific industry example, but I wanted to leave you with a few more example workloads with customers that we see being successful running their HPC applications on AWS. One of the ones that I think is really interesting from a future sustainability standpoint is Wisk Aero and what they're doing with their eVTOL aircraft, and looking at kind of reconceptualizing what does the future of flight look like. If you imagine electrified flight and the challenges that come with that, with battery densities and such, and they're performing multiple workload runs on AWS. Commonwealth Fusion Systems, future of fusion power, that seems pretty compelling given our increasing power requirements for data center usage that has grown exponentially over the last couple of years with the growth of generative AI. Rivian has been a great partner, and when you see what they're doing around safety testing as well as the designs of future vehicles for electrified transport, extremely interesting. 23andMe is scaling up to hundreds of thousands of vCPUs running via AWS batch when they're looking at their gene sequencing algorithms. So there's a customer use case that can fit almost every workload. So if you have a question about how your particular case or workload could work on AWS, please reach out to us. We've probably got an exemplar that we could work with you to partner with them to see how they were successful. We've got a broad partner ecosystem. So from, pick your favorite chip vendor. One of the things we talk about frequently at AWS is we're all about choice. So I know sometimes that can be both a benefit and a chore. When I say we have 850 instances, some customers get really excited, some customers go, how do I know to pick the right one? And that's why we have the right side of the slide for our consulting partners. So we have partners that will work with you that have built pipelines and orchestrations specific to various industries to where they can work with you on what is the optimal instance and cluster architecture for your system to be successful. And then I can't end without at least bragging on my team a little bit. At the recent supercomputing conference, we were yet again awarded with the best HPC cloud platform, now for our 7th year, and for a total of 6 awards, including one for the service that we talked a lot about tonight, AWS PCS, for one of the top 5 technologies to watch in all of HPC. So I think it's really exciting to see what customers are going to do with that service, and we look forward to getting your feedback on how we can continue to improve it. So I'll just leave you with this challenge. What are you going to do with composable, dynamically allocatable resources to improve the cycle of innovation at your place of work? Thank you. If you have any, we'll be up here taking questions at the end, but if you don't have time to have your question answered, please reach out to Michael or myself. You've got our contact info up there, as well as it's super important that you fill out the session survey. That helps us know how we can do better next time. And thank you for your attention and for your time.